One of the places in which systems show up as being useful to us, and to be frank here, this is a useful thing for us to have eventually in like a calculus 2 class. We would have to have passed through and be comfortable with some very standard calculus before we got to some more advanced calculus, where this is going to be a helpful sort of idea to incorporate. And the idea here is partial fraction decomposition. Basically what we're talking about is we can take any fraction and try to split it apart into adding and subtracting less nasty looking fractions, nicer fractions, fractions that have prettier numerators and denominators. What we would like to do really, it does kind of come down to the denominators. What we'd like to do is we'd like to come up with fractions that have the nicest possible denominators. So we want to try to downgrade our denominators as much as possible. And so largely what we've got going on here is going to start with what sort of factors come out of our denominators. Now, because of the nature of fractions, there are different possibilities, different cases that we would have to talk about. So, talk about the one that's like this example here. The degree of the numerator is smaller than the degree of the denominator. If that is the case, then start things out with looking at your factor denominator. The kinds of factors that you see are going to control the kinds of fractions, partial fractions, that you're going to build. So if you've got a linear factor, something that is like an ax plus b, then you are going to build very mellow kinds of fractions. The numerator of these fractions is just going to be a constant. And we don't know what that constant is, so we've got to make sure that we're using enough different kinds of labels to set these apart from one another. So the first numerator, capital A sub 1. The second numerator, now if we've got this linear factor with any sort of power attached to it, like parentheses, 2x minus 1, parentheses to the third power. Well, now I need to use just the regular factor of 2x minus 1. I would need to use 2x minus 1 parentheses squared. I would need to use a 2x minus 1 parentheses power of 3. So I would have to actually have this extra level of complexity to represent the different possible ways of things all working out. So we just keep on slapping different constants up there into those numerators until we've dealt with the highest power that showed up. If I've got a different linear factor, I do the same thing. But what if I don't have a linear factor? Well, then that means that, and this is as bad as it gets for us, we would be looking at what we would have as quadratic, because we're not going to make it any worse than that. And it's not something that can be factored. Otherwise, we would have done that already. So we refer to the non-factorable versions as irreducible quadratic factor. So whatever that quadratic factor is, now again, that could be a power that's attached to that outside of a set of parentheses. So again, I'm going to want to represent with my fractions those different possible denominators having those different possible powers. And this time, instead of just a regular old constant up on top, my numerator is 1 degree lower than my denominator. So if my denominator is quadratic, my numerator up here has to be a linear expression. So a1x plus b1. And because I would want to have these different letters being used, a2x, b2. So again, all of these numerators are going to be linear expressions. They're all going to be different. So that's how we would try to set things up. Now with all of these different numerators showing up, we can eventually work our way through and figure out a system of equations that will allow us to figure out what those individual numbers are that show up in those numerators, whether those numerators are constants or linear expressions. So that's where systems will show up. Before we can even do that, though, we've got to mention what happens with the other possible fractions that we might have in our original problem. So we can just kind of say, look, if it's not the degree of the numerator is smaller, let's just say case 2 handles both the degree of the numerator is equal to or it's greater than the degree of the denominator. Well, now here's where we come in with the long division, because we're probably not going to have a nice enough denominator to use synthetic division. We're just pretty much already kind of going with that pessimistic view of things, like, oh, dang it, we're going to have to do long division, and whatever our remainder is, and our original denominator, that is at least taking us back to case 1, where the degree of the numerator is smaller. So the long division helps us kind of break things down. Then, like I said, we're going to need to determine all these different A's and B's, and that stuff's going to come from systems. Let's look at a couple of examples of how things can work out here before we get into how the systems are actually going to churn out. So first of all, we got to make sure that we're putting the rules together the right way with these generic partial fractions. Giving us a factored numerator makes things a whole lot quicker for us. So we see that we've got two different kinds of factors down here in the denominator. We've got, actually I just think I said factored numerator a minute ago, giving us a factored denominator here being, real nice. We've got two different factors that show up down there in the denominator. We've got the x squared plus 1, can't be factored anymore, so that's quadratic. We got the x minus 2, that's linear. So our rules tell us, first of all, deal with the linear stuff because it's a little bit more mellow. We would need our linear factor by itself. We need a constant up on top. Because our linear factor has a power, then I'm going to need to bump that until I get as high as the power goes. So power of 2, power of 2, give me a constant up on top again. Power of 3, that's as high as it goes, so this is where I stop. But again, my numerator is a constant. The other factor is quadratic, and so the numerator has to be 1 degree smaller, so the numerator has to be some sort of linear expression. Since I already used a capital A, a capital B, and a capital C, I'll use capital DX plus capital E to represent that fraction that could show up, and all of these generic fractions would be added together. I would eventually want to be able to find the A, the B, the C, the D, and the E. That would mean that I would need as many as 5 equations to handle the A, B, C, D, E. Whew. Thank goodness we've got matrices to handle things with the calculator. Try to make that as quick and painless a process as possible. Now, we're not going to do that quite yet. We're going to, again, kind of focus here on what sort of possibilities we have showing up for these different kinds of partial fractions. So here's a little something that's different in that all of the factors that show up in this denominator are linear. Are they really? Yeah, they are. X minus 1, definitely linear. X plus 2, definitely linear. X squared, well, isn't x squared quadratic? True, it's quadratic, but can it be factored? Well, sure it can. X times x. Linear. Linear. Constant on top, constant on top. Because the x has a power on it, I need a regular x in the denominator with a constant in the numerator. I need an x squared in the denominator with a constant in the numerator, and string those 4 fractions together through addition. And in this particular case, because I've got 4 different letters that I would need to work out for those numerators, I would need to end up having at least 4 equations. And again, I would want to solve that system as quickly and effortlessly as I can get away with, so that I can get those values that I would need. Again, We'll get back to that sort of thing, but for right now, we're just worried about setting things up. So let's talk about how this would work. Can I get this all in at once? I can. There we go. So that earlier fraction, I just automatically slapped down the numbers that we would need and said we would have a 1 and I think it was a -1. How on earth would I have come up with those? Well, I would need to go through this partial fraction decomposition and set up these generic partial fractions. I would have one partial fraction for each of the factors because those factors don't have any extra powers on them. Each of those factors is linear, so each numerator is a constant. That only gives me two numbers to figure out what the A is and what the B is. In order to figure those out, I'm using this equation. I'm going to multiply on both sides by that denominator so that I can get rid of those denominators and try to come up with a way of putting things together so that I can match up my original fraction, which has a 2 on top, with these new fractions. One has an A on top and the other one has a B on top. By clearing out the denominators, we end up with this particular equation. This equation has both x's and constants. And so if I combine my like terms, my x stuff is going to have to match up with the x stuff from my original numerator. There is no x stuff. So a plus b is going to have to be equal to 0. There is no x stuff. My constant stuff is a 2, and my constant stuff in this equation would come from the a minus b. So that gives us two different equations to build and have as our system, and then we can solve the system and come up with those particular values, 1 and -1, which means that we could rewrite that as I had originally given it to you as a subtraction problem, like so. Whatevs. Now let's do this one full out, start to finish, so that you can see how everything goes. Now, like this previous example, notice that the first thing we did was comment we are going to set up the decomposition. So we're going to even make that same sort of separation here about setting up the decomposition. The first denominator factor that we see is an x. It does not have a power. According to our rules, that means that we are going to have, how do we do that before? Yeah. That means that we're going to have, let's write the original expression down. We're going to have our first partial fraction with a denominator of x. Because our denominator is linear, our numerator is a constant. So, the denominator has a factor of x. That is linear. That means our numerator is a constant, a. The x does not have a power, so I do not get any more fractions that come from that factor. The other factor that we see is x squared plus 4. It does not have a power on it. So we are going to get one more partial fraction that uses the denominator of x squared plus 4. Because that denominator cannot be factored, it's quadratic, that's going to mean that my numerator has to be a linear expression. And so let's call that bx plus c. We would take these two individual fractions and we would add them together. That's the most straightforward thing to do for this kind of generic setup. That's the setup. Here are our partial fractions. This is what we would work through if we were required to do the full decomposition. So if we were just asked to do a setup, that's that. There's the setup. This is what those partial fractions look like. That would be all done. But our instructions in this particular example do have us doing the full decomposition. So now we're going to want to figure out those values for the A, the B, and the C. So let's again kind of model it after the previous example there. Now find values for A, B, and C. We are going to take our original fraction and we are going to multiply by its denominator. So again, to just kind of call out to that there, in a separate color, we're going to multiply by the original denominator, which would be an x times x squared plus 4. We are going to take our partial fractions and also multiply by that original denominator, so all of that stuff is going to be multiplied by the x times x squared plus 4. On the left-hand side, those denominators cancel out and leave us with x squared minus 2x plus 3, that original numerator. The first fraction times the stuff in blue allows us to slash out the x, but we'll still have the a and still have the times x squared plus 4. Plus sign there. From the second fraction, we would have the numerator bx plus c. The x squared plus 4s would get slashed out, but that would still leave me with the x also appearing. Now if we go ahead and we do the multiplication here, then that means that we're going to get a x squared plus 4a plus bx squared plus cx. Now let's go ahead and rearrange those things so that we would have our ax squared plus bx squared. These are like terms that we can actually write as parentheses a plus b parentheses x squared. We would have our x term, well that's just a cx, so thankfully that's not getting too awful crazy. And then we would have only one constant showing up with the plus 4a, so thankfully things here are not getting too awfully crazy in terms of how much stuff we've got. But in order for this to actually be useful, we're going to have to match the left and right hand sides together. So let's use a little color coding to help us out. 1x squared. Over on the right hand side, we've got not a 1, but an a plus b in parentheses in front of our x squared. Minus 2x So in front of our x term, we've got that orange minus 2. Over on the right-hand side, in front of our x, we have a plus c. So the color coding is going to end up helping me match stuff up. In purple, we have a normal plus 3 over on the left-hand side, and on the right-hand side, our normal number stuff would be represented with the plus 4a. So pink with pink, orange with orange, purple with purple. 1 is going to match up with the a plus b. So this is allowing us to now put together our system that will allow us to find the values of a, b, and c. So in pink, the 1 is equal to a plus b. In orange, the negative 2 is equal to c. And in purple, the positive 3 is equal to 4a. Now this is designed to be not too awful bad. Based on that bottom equation, I can get A, and based on the pink equation, I can get B. C is already flat out showing up with no extra effort involved. So, trying to keep things a bit on the mellow side to at least demonstrate the idea here. A would be equal to 3 over 4. Then that would mean that our equation a plus b equals 1 would become 3 over 4 plus b equals 1. So b would be equal to 1 over 4. So there's our a, there's our b, and as we already said, c is just flat out popping out directly from our established relationships. So this now gives us, we've got enough room down here, the original fraction, x squared minus 2x plus 3 over top of the x parentheses x squared plus 4. Originally had this set up a over x. So that means if a is 3 over 4, we can write in 3 over 4 over top of the x. That's a little awkward. We'll tweak that in just a moment. The other fraction that we've got has a bx plus c. Well, we have figured out that the b is a 1/4 x. The plus c is really a minus 2. And down here on the bottom, we would have this fraction with a denominator x squared plus 4. Now, arguably, this is a little awkward looking, having fractions in our numerators. So the way that we can get rid of those and get something that's a little bit more natural is if we go ahead and multiply by 4 on the top. That would give us 4 times 3/4 is 3. Multiply by 4 in the bottom, we would get a 4x. For the other fraction, we would also, as it happens, want to multiply by 4. 4 times 1/4 is 1x. 4 times the negative 2 is a minus 8. 4 times the denominator, well, look, no need to be fancy about it. Just go ahead and put the 4 out in front of a set of parentheses with the x squared plus 4 and just call it a day. Ain't no need to be any fancier than that. If we took the time and trouble of doing this addition with fractions, we should find that we would get the x squared minus 2x plus 3 as our numerator. So There is a way. It would require a good deal of time and effort maybe to check it, but there is a way for us to actually check that this is the correct decomposition that comes from all of the work that we've done. So it's better than nothing, but hopefully we don't necessarily have to do too awful much of these, because frankly, while it's a use for the systems, there are other uses that you would have seen, I'm sure by now, in the homework other than partial fractions. But we need to talk about it, and it shows up later on eventually in the calculus sequence, so you may end up encountering it as you move forward in your math work.